This is the first time we have held a joint session with the Association of Space Explorers and the International Astronautical Federation. Two very famous organizations, and we are working together now on this particular session here. And in fact, the Association of Space Explorers is delivering a special plenary in Jerusalem in 3 weeks from now at the International Astronautical Congress. So it's reciprocal work that we're doing together with each other. Now, let me tell you a little bit about the format today. There will be 4 speakers of approximately 15 minutes, followed by 5 minutes of questions for each. And then at the end, we have planned to have some extra time when we will have all 4 of the speakers come back up here, and we'll have sort of a group discussion and group Q&A with the audience. So I'd like to introduce my co-chair to you, and this is Kristen Bank, and he is chairman of the Human Spaceflight Committee of the International Astronautical Federation. He's also head of process management and certifications at Airbus Space and Defense, which must be quite a task in itself. Now, Kristen joined the Human Spaceflight Committee in 2009. However, because of his expertise and actually his enthusiasm, it was only 2 years later that he became chairman of that committee. So, Kristen, I would like you to have an opportunity for some opening remarks.
Thank you very much, John David, for introducing me. So, good afternoon to everybody. And thanks again for this initiative to organize this joint session. And it's a great honor for me to represent the IAF and the Human Spaceflight Committee at this occasion and to join ASE yesterday and today. Actually, I realized once again how famous you space explorers are everywhere around the world when I came to the Grand Hotel yesterday early afternoon, and I found a huge crowd standing there in front of the main gate. And I thought, wow, Kristen really has sparked the flame here in Sweden. Later on, somebody speculated that there was Bono of U2 also staying in that hotel, and that maybe some of the people were waiting for him, but I think that was a minor share of them. So, astronauts attract a lot of people, obviously. People of all ages and all cultural and educational background. Even those who sometimes would not care as much about technology, science, engineering. But what is it that you explorers stand for in the eyes of so many people all around the world? The fascination of meeting one or even many of you obviously does not depend on your nationality. In some cases, your specific mission, your individual accomplishments, may add a special touch, yes. Somebody who lived through a very long duration flight, who experienced extravehicular activity, even flew freely in space 100 meters away from a spacecraft, or made it beyond low Earth orbit, may receive an extra bit of admiration for his individual courage. But after all, cosmonauts, astronauts, taikonauts, they're altogether a very special group of people for the people around the world. I believe that it's not so much about where you went to, but where you came back from. That place where there's no national boundaries, no local history that attributes any place in space to one particular nation, or that could blindfold us and our minds against collaboration. Just creation itself. And no man-made interpretation of who did it and how we are supposed to understand it. Since you came back from that unclaimed territories, people take you as the true ambassadors of all people around the world. You may have gone there for one nation, but you came back in peace for all mankind. As one of you put it, I quote, "You develop an instant global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it, unquote. And another one said, again I quote, "On the first day, everybody pointed to his country. On the second day, to his continent. But on the third day, we just saw one Earth." So in these days, as we look around and we find an increasing tension again, where we had hoped to overcome power games and had looked forward to long-lasting collaboration and mutual benefit, maybe this is one of the most important insights, aside from the technological and scientific one, that you can bring back to Earth. And it is in this spirit that I have a personal dream that one day space explorers will not only carry the flag of their home nation, but also the one of the United Nations. And they will do so with the same pride and the same dedication as the one of the country they came from. But admittedly, that is a very long-term dream. So for today, I wish all of us a very interesting and intriguing afternoon with our distinguished speakers. And I would like to hand back to John David Bartow to introduce our first speaker.
Thank you very much, Kristen. Thank you for your introduction. We appreciate that. So our first speaker is in the upper left corner of this chart here, and obviously he needs no introduction to you folks. As being the Director General of ASE, he is the Bolshoi banana of ASE for 15 years, now retired. And it's a real pleasure to have him come talk to us here today. So you may know him as the former Director General, but I'm not sure how many of you also realize that he is a true-blood rocket scientist, okay? So some 40 years ago, he wrote a paper about the pogo effect in the European rockets that were being developed at that time. And it was so impressive to rocket scientists around the world that he was invited to come to the United States and work on some of the problems of the shuttle main engines back at that time. So we have here a true rocket scientist with us. Now, we met about a little more than 25 years ago, and we were working on the early agreements for the International Space Station. And although we were on different sides of the table, we developed a pretty quick friendship, and I think that had to do with the fact we both have two first names, and we both put a hyphen in between. So Jean-Jacques, you have the floor.
So it's a real pleasure for me to be with you today. First of all, because of the place, Stockholm, which is a place where, this is the only place where I have taken some leave in the last 25 years. Because of this year, because it's a very special year. First of all, this is the year where we have all celebrated the 50 years of the first walk in space by Alexei Leonov, but also the year during which astronaut Padalka has broken the record of the number of days spent in space, more than 2.5 years in space. I must say that bravo. But it's also a year during which we shall have 3 ESA astronauts on board the space station with Samantha, Andreas, and at the end of the year, Tim. So just to say that this is a special year. But more than that, the event, so many space explorers together, astronauts from all over the world, making of Stockholm the biggest international space station on ground. So, as you know, I would have preferred to be among you. My dream has always been to be an astronaut, and still is. This morning, I have heard that a lot of people were inspired by space. Myself, I must say I was not even inspired. I always thought that I had no choice. Just to say that I have entered, and this is true, you can check, I have entered the secondary school in France on the 1st of October 1957, And the Soviet Union was so glad that I entered the secondary school that they have launched Sputnik on the 4th of October. And I have got my engineering degree on the 20th of July 1969. And this is because of that Neil Armstrong was so glad that he put his foot on the moon. So just to say that I had no choice but to be in space, and I may be retired from ESA, but I am not retired from space. So just to say that I am very glad to be with you, and I am so glad that I took the liberty to not to do what John David asked me. He asked me to speak about the advance in Europe space capabilities. I must say that the next speakers will address that, and they are much more documented than I can be, because for me the most important advance in Europe's space capabilities is the fact that there is a new Director General at ESA. Jan Werner is now in charge. Maybe just one aspect of what ESA has done in the last several tens of years. We have always had three objectives at ESA. First, to push the frontiers of knowledge, and that this is all the science that we are doing, and that we are doing in partnership with international partners, with United States, with Russia, with China, with India, with almost all space powers in the world. The second objective is to develop new services for citizens, and we are doing that in partnership with EUMETSAT for meteorology, with the European Union for navigation and environment, just to say that it's a lot of partnership also. And the third objective is to support the competitiveness of European industry, and we are doing that in partnership with industry, in particular for telecommunications and launch services. Meaning that the main characteristic of ESA is that we are not doing anything alone. We are doing everything in partnership. And as I said many times when I was ESA Director General, if there is one point that ESA can teach the world, it's cooperation. And this is the reason why I shall focus my introduction on humans and space. Not humans in space, because humans in space is too easy. I shall speak of humans and space. And clearly, humans and space, they have the same origin and the same future. And just because planet Earth and we, the humans, we belong to space and not the other way around, meaning that space is our origin and our future. Humans have always used space, always, to understand who they were and where they were, and to improve their life on planet Earth. The link between humans and space before they could go into space has been the light they could see, and especially at night. This was the way they were looking at space. And it took centuries for humans to understand, and even more time to accept, that planet Earth was not the center of the universe. And it took centuries for humans to use these lights to measure time and to guide their travels. Today, all humans are using space every day, and they will continue to use it more and more to understand, to improve quality of life, and to contribute to growth. Going to space has improved our understanding of our origins. Just two examples made in ESA, and that I had the privilege to live during my mandate of DG. So Planck, I don't know how I can use that. Yes. Planck, which has given the fossil light after the Big Bang. And as I said many times, we are all coming from there. You are there. It was 13.8 billion years ago, but we are all coming from there. And the second one was Rosetta, and my colleague will speak much more about that. So this is the famous selfie of Rosetta with the comet backwards, and that, which is the landing of Philae on Rosetta. And we are also all coming from there. And it was only 5 billion years ago. So I think that you have seen you 13.8 billion years ago, that it was 5 billion years ago. So it took some time to come from these two pictures. It was a long way between these lights and today. We have understood just a little bit of the processes which came from that time to today. But obviously it's only very little steps in our understanding. There is much more to do to discover and understand that we have done so far. But in spite of the fact that there is still a lot to do to understand, and for the young generations, don't worry, you will be busy. But space has already brought three important messages, three essential messages, which are vital for the future of humans on planet Earth. The first message is that planet Earth is finite, meaning that natural resources on planet Earth are not infinite. The second message is that planet Earth is one, meaning that our future on planet Earth is collective. There is no individual future on planet Earth, meaning that we have to share these natural resources. And number three, planet Earth is unique, meaning that there is no planet B, that this is what Monsieur Ban Ki-moon is saying, and that our future is definitely linked to planet Earth. Obviously, we could have known these three messages without going to space. But the fact is that sending humans into space, and in particular around the moon, has provided witnesses who could report what they have seen. And pictures are always much more stronger than words. Witnesses are much stronger than rationals, science, and books. And this is in that sense that for me, and I have always said that, for me Apollo 8 has been a breakthrough in the history of humanity. The statement of Bill Anders when the crew was coming back from around the moon, we made all this way to explore the moon, but the most important thing is that we discover planet Earth, is the most important heritage of the Apollo program. And it is so true that it took only 3 years. 3 years. After Apollo 8, for the famous Meadows report to be issued. And this report was called The Limits of Growth in a Finite World. And I am sure that there is, it's not by chance, that there was the Apollo program and there was the Meadows report in 1972. At that time, when the book was published, it was not really considered. But I can tell you that today, it's almost every week that there is a book which is issued exactly on the same subject. So just to say that 40 years later, the report of Meadows is very up to date. So everything we are doing in space has one objective only: planet Earth and the future of humans on this planet. And astronauts have a great responsibility. Great responsibility. Because people believe only in people. Because they are like themselves. Today I was in a hotel in Gamla stan, and there is only one picture on the entrance of this hotel, is that this is the mark given by the customers of the hotels, because the customer, they believe only in customers. And this is a good hotel according to the picture. So, but just to say that people believe only in people. And this is where the astronauts are so important. Because people, they believe less and less in institutions. They believe less and less in managers, even less and less in their fathers. We can regret that, but this is just a fact. So I shall come back to that on the responsibility of astronauts. So space is not only important for today's life, it is even more important to make life possible on planet Earth in the long term. There are a lot of threats on us. I shall not list all the threats. Some of them are coming from us. Some of them are coming from space. But anyway, there is a lot of threats on the sustainability of life on planet Earth. It's no use to worry. It does not help. We have just to take actions. Unfortunately, the process and even more the calendar are uncertain, which make most of the people confident, and especially the politicians, because the calendar is not known, so it's good news. But this uncertainty should stimulate those who manage the uncertainties for pushing the frontiers of knowledge. And we, the space people, we are there to manage the uncertainties. Our job is to push the frontiers of knowledge. So we are the managers of uncertainties. So we are the ones to take action. We are the ones to make the impossible becoming possible. So, you astronauts, who have made the impossible, you have to help, to move, and to act. Because all pretexts are used today to postpone any decision. Not only for space, by the way, but for a lot of things. And it's a paradox to live in a world where everything is faster and faster, and where decisions are slower and slower. Yes, I know. I know because there is enough communications on that. I know that there is currently a lot of private investments made in space these days. And this is good, very, very good, and positive for many reasons. First, because it brings new actors, new approaches, new methods. Number two, it reduces the time for decisions, and it reduces the cost. It has already brought significant achievements and great success. It feeds and sustains communications on space. It forces other actors to move. So all that is very positive. And this is the reason why I am thanking those who are currently investing in space. But it seems, by doing that, that we are making an opposition between new space and old space. And that is very strange, because there is only one space and one future only. There is not a new future and an old future. And still, the sum of private investment is still a very few percent of the government investments. Today, according to the books that I am reading, there is $3 to $4 billion invested in space per year by private investors, which is fantastic. But there is still $70 billion invested by government in space, meaning that this is just a few percent. And unfortunately, this few percent, which is very good, gives a pretext for government to slow down their decisions. Let's reflect. Let's see. But that is something that I would like to counteract. Because slowing the decision of the government is not good for space, including for the private investors, because they take benefit of the government investments. So it does not help the global space activities. So this is the reason why we have to do something, and you have to do something. And especially because the most interesting part of the private investments is a storytelling of investors. Listen to them. Most of them claim that their objectives are connected to humans in space. Elon Musk has only one objective, which is to put humans on Mars. Let's say the Falcon 9, everything is just intermediate step. The goal is to put a man on Mars. Richard Branson is to send tourists in space. Monsieur Bigelow is to ensure a permanent presence of humans in Earth's orbit. So they are all interested by humans, which is a clear demonstration of the importance of humans in space, because this is the best way to promote the link between all humans and space. So the future is made of uncertainties. And in the world which is faster and faster, the uncertainties are becoming bigger and bigger, meaning that the world is more fluid than solid. Antoine de Saint-Exupéry was already translating that in his book, Citadel, in the midst of the 20th century. He has written, the future, you have not to predict it, you have just to make it possible. And in spite of the uncertainties, I am certain of two things only. That the two fundamentals to make the future possible for humans on planet Earth are, number one, global education, meaning educating each and every child in the world. And number two, global cooperation, meaning building up cooperation at worldwide level, not excluding anyone, not excluding any nationality, not excluding any expertise, not excluding any generation. Education of all children is key for a better world. Yes, we need certainly the best talents to continue to push the frontiers of the possible. But more generally speaking, obscurity is generated by a lack of education. By the way, I have said that the natural resources on planet Earth are finite, except one, the brains of our children. This is the only true renewable natural resources. But the brains of our children, we have to transform the natural resource into something intelligent, which is the role of education. And so I don't fear a shortage of brains, but rather a shortage of education of these brains. The second fundamental is cooperation, involving everyone on planet Earth, which is also a key for a better world, since our future is collective. So it's a cooperation among countries, among nationalities, among expertise, among generations, and especially between the new generations, which are upstairs, who have not met yet the frontiers of the impossible, and the experienced generations, the old ones, which are below in this room, who have spent their lives to push the frontiers of the possible. Each generation learned from the others. So there could be a competition among generations. I know that. The young, they want always to take the position of the old. I know that. Place aux jeunes. And the old, they would like to have the age of the young. That it's, but even if there is a competition between the young and the old for the short term, in the long term, this is the role of each generation to make the life in the long term possible. This is our collective challenge. So this is what we have to do, that we have to do together. And it's time to conclude with you, astronauts, because you are both essential for education and for cooperation. For education, and I was glad to hear this morning that you will visit a lot of schools and universities during this week. But you have to do that not only during 1 week, but you have to do that every day. Because you astronauts, you have always been a model for children. I have read during the summer a book, and when I see what Monsieur Yuri Gagarin was writing to the children, I must say that this is fantastic. This is fantastic how Yuri Gagarin could be attractive for the children. And I know that you, astronauts, you are attractive for all children. And at each flight of ESA astronaut, we are always organizing connection between the astronaut in orbit and the children. And this is certainly one of the most successful activity of the astronauts in orbit. And you have to teach to the children that the expertise is not only technical, the expertise is also human. There is no real expertise without human expertise, because this is the only way to cooperate. We are cooperating among humans, so you have to teach the human expertise. And cooperation, human spaceflight have always been the field of cooperation. The competition was only for 10 years, since it took only 6 years between Apollo 11 and Apollo Soyuz. Apollo 11 in 69, Apollo Soyuz in 75. And then there was the flight of non-Russian astronauts on Mir. And then there was the reunification of Space Station Freedom and Mir 2 into the International Space Station. So all that has been a signal of cooperation, and that this is the International Space Station. And as I shall quote Mike Griffin has always said that the partnership of the International Space Station will last much longer than the hardware. What we have built together is something which will stay forever. But obviously we have to continue, we have to extend that. We have to extend that to other countries. We have to extend that to other people. And this is the reason why we have to act now. And there are so many pretexts not to take actions. I must say that the story of do we go to the moon, do we go to Mars, do we go to the asteroids, I don't care. We go everywhere. No use to spend years to decide on where we shall go. We have to go everywhere. So don't let you locked into debates which are there only to postpone decisions and actions. So you have a lot of responsibilities, my dear astronauts, for making the future possible on the planet Earth. You are not alone. I shall take my part. And I have some projects in education, in international cooperation. But even if you are not alone, you are unique. You are unique because you are witnesses. Nobody can replace a witness. You can report what you have seen. You can report what you have done. You can report of everything you are doing in space, which is important on planet Earth. You are unique because you can report on the necessity of international cooperation, on the necessity of education, of human expertise. You are unique because you can share your dreams. So nobody can replace you. When I was Director General, I always said when I am on a podium with an astronaut, nobody cares about the Director General. And And this is true. This is true. So enjoy your meeting, you, the astronauts, but please do not exchange only your souvenir, exchange on making the future on planet Earth possible. Thank you.
So it's no surprise to me that Jean-Jacques took a different tack than what I expected him to. That's pretty standard for him, for those of you who have heard him speak before, and I really do appreciate that. A fantastic motivational speech for all of us sitting here in front. I hope you were listening carefully. We have time for a couple of questions for Jean-Jacques, so who would like to start?
Jean-Jacques, thank you very much for the thoughtful presentation. You talk about our responsibility, and I totally agree with the fact that we are a unique group who has a unique responsibility and to some extent a unique opportunity, perhaps because of that. At the same time, you mentioned the new initiative which is coming out of the private sector, and to some extent you hinted at the increased reluctance of governments to act as a result of this. This group of which we're members perhaps is the most closely linked with the planetary nature of life as opposed to the national or local affiliation with life or the association. I wonder if you might comment on how you believe we can get governments moving more effectively on planetary level issues as opposed to those which serve merely national prestige. And I think in particular of the responsibility this organization has taken toward protecting the Earth from asteroid impacts and the lack of success to some extent that we have had in getting governments to act, and in particular to act cooperatively.
Yes. First of all, it's not because you are not successful the first time, the second time, that you have not to try again. I have been a professor, and I know that the only way to make you understood is to repeat. And again, yes, I agree with you. I am the first one. I have been Director General until the 30th of June last, which is not too far away. And I was the first one to regret that we could not engage our respective governments to look at global exploration. I have worked on that, but I was not successful. But I shall continue. Obviously, I have not the aura of an astronaut, but I shall continue because I am a strong believer on that, and I am even more and more a believer in that. And this is the reason why I think that the community of astronauts, you are representing more than 20 countries and certainly more, you have an impact which is invaluable. But in my view, speaking just to the government is not enough. I think that we are living in a world now where the public sometimes has more power than governments, and this is the power of the multitude. And this is where I think that, and especially the young generations, myself, I would work even more on the young generations. I would spend more time with the young generations at worldwide level, not only the American, the European, the Chinese or the Russians, worldwide. I think that you have certainly a big impact in countries of Africa, of South America, and so on, and that should become a worldwide movement to create some momentum. It will take a lot of effort. It will take a lot of energy because, as I said, there is so many pretexts not to move. But try again. And if I can help, I shall be with you. I am with you.
Thank you very much. Thank you so much.
Our next speaker is Gerhard Thiele. He was born in 1953, and he went through 3 very difficult educations. First, he became a physicist, studying in Munich and Heidelberg. Then he became an astronaut and flew in February 2000 on STS-99. And last but not least, he's a father of 4 children. He currently is now, in the years until his retirement, in the Office for Strategic Planning and Outreach of ESA in the Directorate of Human Spaceflight and Operations. Gerd, welcome to the stage.
Thank you, Christian, for for the kind words as an introduction, and Jean-Jacques, you really haven't made my life easier here. For 2 reasons, the setup is a little bit strange, because I was asked to talk about the European Space Exploration Strategy. And here sits the Director General of ESA for the past 12 years, who just admitted that he has not succeeded in convincing the governments to join in global exploration in Europe. What I'm going to tell now is, the way I see this, and that would be my very first answer, we may have failed in the ambition with which we set out initially. My take on it is exploration will succeed. It may not succeed as quickly as we all wish at times. And as Jean-Jacques has mentioned, I have taken exactly the same. I was given a certain task, and then I thought I probably revise it a little bit. My retirement is only 3 months away. So I thought maybe instead of reporting to you dryly what the European exploration strategy is, I give you my personal reflections as an astronaut and an ESA staff member who is just 3 months before retirement, which gives me probably some liberty to inject some ideas that you normally would maybe not do. But before we talk about the strategy of exploration, I need to tell you first what is exploration. And now you witness an astronaut without any training, so that was the wrong button. Here we go. Okay, we all have an understanding of what exploration is, although it is very difficult to define what exploration is, and I'm not going to define what exploration is. I will not make this attempt here, but if I give my personal reflections, you should understand how I see it. And we haven't talked about this image, Jean-Jacques and I. He mentioned Apollo 8, which changed the game, and it was the same for me. This image really changed the way I looked at the world. And what comes to my mind immediately is a word of Antoine Saint-Exupéry. Man sieht nur mit dem Herzen gut, das Wesentliche ist für das Auge unsichtbar. You only see good with your heart. The important things are invisible to your eye. I think that image really shows what is behind that sentence. For me, it is all a difference that a human being took this image and not a robot. So that is one aspect of exploration. And the other one, that is this one. And exploration is not only humans, of course. And everyone who was here in Europe, and probably not only in Europe, was excited when Rosetta finally arrived at the comet Churyumov-Gerasimenko. I'm not going to talk about that. Andreo Akomazzo from ESOC is here, and who will do that. I promised to him that I will cut my speech short so that he has additional minutes. Please take note of that, because he has very interesting stuff to tell you. But it certainly was an endeavor that made me proud to work for the European Space Agency. But nevertheless, with these 2 images, one thing is missing, and that is this one. Sometimes life is really interesting, because when I entered the Grand Hotel yesterday, into the elevator, who comes out of the elevator was this gentleman. Bruce, where are you? Here. Bruce McCandless. For me, this is the image that tells the story that Jean-Jacques just mentioned. Humans and space, but humans also belong into space. And I would not be an astronaut if I would not phrase it like that. Now, when I have given you the way I look at exploration, some words on the strategy, and before I share with you a few details of the European strategy, I would like to report quickly about two statements that I heard from administrators and director generals. In 1996, I am fortunate enough to be a member of the Sardines, the NASA astronaut class 1996. 7 of them are here. I think we are the biggest class, is that correct? Represented here at least today. Yes, Spanky. And I will not disclose who the NASA administrator was at that time, but a training took us to all the sites at NASA, and we met the NASA administrator, and I forgot what the problem was between ESA and NASA at that time. But I will never forget the statement that he made: the Europeans will come along eventually. So, the Europeans will come along eventually. I forgot what it was about, to be quite honest. I don't know whether it had to do with rockets, with the space station, but that sentence sticks with me. And it shows me that the world looks at Europe a little bit different than the Europeans look at Europe, which makes, of course, a lot of sense. Now, the other statement highlights that from a different perspective, and since the person is with us in the room, I can disclose the name. It was Jean-Jacques. And that was on the 6th of December in 2007, if I am not mistaken. And it was the attempted launch of Columbus, which then in the end had to be scrubbed into 2008 and so on. But the statement that got me there was, I don't know whether you still recall when you addressed the people. Before we arrived to this point, we had to talk to 50 governments, 50, in Europe over the course of the program. Europe is different than any other partner in the in the ISS program. Many countries in Europe participate, and all these governments don't stay the same over the course of the program. And in some areas, the changes happen rather frequently, making the life of the agency not necessarily more easy. That is another thing that one needs to take into account, and that, of course, also shapes my view on the efforts to come up with a space exploration strategy. And having said that, we do have, I wouldn't call it really an exploration strategy, but we have a solid block, or we have solid building blocks out of which a strategy eventually will develop. And everything was mentioned. ESA has always, as the first attempt, tried to push the frontier of knowledge. You see it, it is one of the guiding principles in the strategy. Global cooperation is key to the European Space Agency and to Europe as a continent and as a society. So also that should not be a surprise. Innovation is important for our economy to grow and to survive, and Jean-Jacques has mentioned as well. And about inspiration, I do not need to talk. By the way, not only astronauts inspire the young generation. Is Frida here? Christo, do you know? I can't see her, but she was supposed to be here. But that was the most inspiring talk that I heard this morning. And if you are here, I would like to thank you for that. So inspiration, the inspiration aspect, the education aspect is part of it. And to name to you a few things part of this strategy. Europe, of course, cannot decide we will go to the moon and land a human being on the moon. That's very obvious because we don't have a transportation system to do that. So how do you develop a strategy in the situation in which we are in where we hardly can be on these kind of endeavors be the key driver? And the first question that you have to ask yourself is, where do we want to go? And in Europe, we have very clearly identified low Earth orbit, Moon and Mars as the future destinations of our space activities. And what are the building blocks to engage with the various partners? Jean-Jacques has already mentioned that, of course, the United States, Russia, and in the future China and others are key partners for our exploration endeavors. I would suggest to rethink the cooperation with JAXA, with our Japanese colleagues, because if I look at ESA, if I look at the Japanese Space Agency, we have very similar interests, and maybe there can be done more together. One thought from my side. And the other two things I would like to mention in this context, these are personal observations. You always hear and you read it in our strategy as well, the famous term human-robotic partnership. Now, I don't know who has invented it. It probably is, I don't know, something that we have to do in order to be able to sell what we want to do to politicians, decision makers. In my humble opinion, this is a misnomer. I am not aware of any robot who has invented himself to fly, for instance, to a comet. All the robots that are available have been invented by human beings. They are just tools for us to explore. That is how I see them. And if we can transform a little bit this view of human-robotic partnership really in exploration without stressing humans and robots all the time, we might get a step further in the direction that I would like to see. For ESA, I think we see a very good example where we had been successful in the past and where we see elements in the future. Transportation is one part that is important in any future exploration endeavor. And I just quote one example, which is ATV, where I think ESA has demonstrated repetitively 5 times that we have really remarkably on the spot delivered resources to sustain and support the International Space Station. What is the consequence of that? ESA today partners up with NASA on the Orion module building and providing the European service module, hopefully not only for 1 and 2 flights, but for more. So the key thing, and this is also entering our exploration strategy, that ESA becomes the partner of choice for our international partners to achieve what we want to do together in cooperation. And I haven't asked Christian how much time I have left, but I know that I have promised to Andrea that I give some time back with that. I would like to come to a close. And a suggestion, it is not it is not a final answer, but maybe the European strategy includes this term that humans in space and space, we are redefining the possible. Thank you very much.
Thank you for an inspiring presentation. It actually brought some questions to my mind I would like to address to you. I saw a current study by McKinsey, and they've been reviewing the digital leaders of the leading transformative companies of the world today. And the average age of those leaders in these companies and on the boards were 51.5 years old. One wouldn't think that. So what does that tell us? It tells us about the first 50 years of space exploration. It means that these leaders were actually space toddlers, first generation space toddlers, realizing that we can get a man up to the moon and back, and a lot more to it. And now I would like to ask you, because you had three leading words there: knowledge, global cooperation, innovation, and inspiration. But I think maybe what we need to think about too is how has space impact on leadership and governance? And I would like to ask you, looking at ISS as you addressed, what could we expect to be spillovers in governance and leadership in the world? Just looking at Europe right now and the efforts we're trying to make to sustain the problems in the Middle East, it seemed like ISS leadership could do a lot of, could add a lot to that picture. So what should we expect in 50 years from the learnings at ISS? And also the Arctic Council. There are both almost the same countries participating up there, trying to keep peace.
Well, again, I can only give you an answer with respect to that as an educated citizen. And my personal response is, don't overload the ISS with expectations. It is a very dedicated, it's a very complex, it's a very successful project in which 5, and I count Europe now as one, partners are working together. That model is not going to solve all the problems that we are having in our world. And if you expect that, you are asking too much. I would like to come back to one of the sentences that you made in your introduction, and I saw a perfect image this morning, and I forgot in which presentation, a young girl looking, I think it was in Chris' presentation, looking at Chris in space. And what shapes you probably more is what you consider as normal while you are growing up. And we have 3 grandchildren, and I can see it already in them. What is normal for them was inconceivable for me. They will be different, and it will change the way they will handle the world. The other thing, and the only other thing that I can tell you, is we are going to change how we treat ourselves, how we act in our world, only, Jean-Jacques said it, if we cooperate and if we are educated. These are the 2 key things. Cooperation, ISS is one example of cooperation. There are other models which are more appropriate for other tasks. That is my best answer I can give you to that.
Throughout the 90s, Patrick has been involved in various bed rest studies with ESA, but also cooperating with the Russian Space Agency in Moscow. And then he earned his degrees as a physiologist in 1999 and as a medical doctor in 2001. After that, he has been the head of the life science section in the then Human Spaceflight Directorate at ESA for almost 10 years. And he holds a research position at the Unit for Environmental Physiology at the School of Technology and Health here at KTH. Please welcome Patrick.
Thank you very much. Can you hear me? Yeah. So, dear astronauts, cosmonauts, and taikonauts, dear fellow non-astronauts, my presentation will be fairly different from the previous 2 ones, and I unfortunately will have to shorten it a little bit because I was a bit optimistic when I submitted the presentation last week. But the outline and the focus of my talk will be related to medical research, and especially medical research where astronauts and cosmonauts are used as research subjects. So basically research that are being done on astronauts. And I will talk about completed experiments and rather fresh results and application coming out of this research. So this has been research being done on the International Space Station. So originally I was planning to talk a little bit in general on ISS research. I will cut that short and focus on examples of medical results, and then I will go towards the end and talk a little bit about research roadmap for potential future medical research. Just one word on ISS. And so this, I mean, it's been permanently manned for 15 years. There is a crew of 6 all the time. And each of these crews are participating in several experiments that in various areas, but each are also a subject for 15, 20 experiments that are being done on the astronaut themselves. And basically it's a busy place, and there is a lot of research that has been going on for these 15 years. Is increasing all the time when you look at the number of experiments, and results are starting to come out. And these are the slides that I will skip, like that. And I will go directly towards medical research. So I will not say so much right now on the necessity to increase medical knowledge for future human space exploration. What I will talk about is the knowledge that are being gained and the benefit for medical research done in space. And you can basically divide the benefits in 3 broad areas if you want. It's synergistic research and development, which is basically dual-use technology that you develop in order to do medical research, and you then find the use for it on Earth. And since if you're looking into physiological function, you want to do measurements on a subject, and that subject is in space, you can usually not bring up your equipment to space. You need to develop new technology, you need to miniaturize, you need standalone solutions, autonomy, and devices that can be used by non-specialists. And that kind of technology typically will then have an use also on Earth, and I will give several examples. And then it's the issue of maintenance of astronaut health and performance. Any country or organization that have an active astronaut corps, this is a very important area. To take the example of the effects of long duration exposure to weightlessness, with changes in the balance system, muscle strength goes down, bone loss takes place, physical work capacity goes down. And these changes are so pronounced that they have to be actively counteracted just to maintain health and performance of the crew. And so the countermeasure activities, as they are called, to maintain physiological function in crew is something that is actively evolving and being improved, how to counteract these changes. And this kind of knowledge, this kind of technology that is developed to maintain function, physiological function, is typically not only things that are beneficial for the astronauts only, but it's also beneficial for quite large different population groups, like the elderly, for example. And then there is the new fundamental medical knowledge, and that is related to weightlessness. Typically allows you to ask questions, investigate hypotheses in space that you cannot ask or investigate on Earth or in the presence of a gravity vector. So for example, the balance system or the pulmonary systems is very much affected by gravity. When gravity is absent or changed, you can ask questions that basically is impossible to ask on Earth. So what you will also see that a lot of these aspects will come back now in the examples, and there is a large overlap between the areas. So I will just now start, and I will go through different examples of results that have come out from research on the International Space Station in the last, say, 2 to 10 years. So I will start with an experiment in the neurosensory field. It's basically related to eye movement. How is eye movement regulated? And it's well known that the movement of the eye is tightly coordinated with the vestibular system, with the balance system. So you can maintain a straight gaze, move your head in different ways, and you will maintain the gaze just because that connection. Now the question here was, is eye movement also affected by the gravity vector per se? If you remove that, will the way we coordinate and move our eyes, will it change? And it did, indeed it did. So basically the eyes are moving in a three-dimensional coordination system. And when you take away the gravity, that system changes in a way in that it's tilted. So basically the way you move your eyes in weightlessness is different. And that is given them fundamental new knowledge on how the gaze is regulated in the brain. A similar experiment is related to visual perception, and that is a French-American experiment. Perception is different in the sense that it happens in the brain. You get the visual input, and in the brain you have a processing to decide what do you see and what is the shape of what you see. And it turns out that, again, gravity also affects the way the brain interprets vestibular inputs. You assess shapes differently when gravity is gone. You assess distance differently when gravity is gone. And for this experiment with the eye movement, there was also a technical spin-off. You had to develop a quite advanced system to very precisely assess the movement of the eyes, also torsion of the eyes. And this technology and this industry is now providing this kind of measurements to various clinics doing corrective eye surgery. Another area is telediagnostics or telemedicine. Of course, this is central in spaceflight because there is a natural distance between the medical doctor and the patient or the astronaut which is in space. And it's also relevant for medical researchers that want to do diagnostic measurements on a crew in space. So as an example, echographic measurements is very valuable in any settings where you, for example, look into cardiovascular function or want to do images of internal organs. Thing is, with this technology is it's operator dependent. You need to be quite trained in order to do high quality measurements here. And what an American group together with NASA did, since there is a need to do this in space and many scientists were asking for the measurements, they developed over a couple of years a procedure, a structured process where with limited training of the crew and structured guidance from the ground, the astronaut could do very high precision measurements on each other. So this was developed over time, and now this is being used, exactly this process, worldwide in various rural areas. And a quite a large number of health professionals are being trained in doing telediagnostics, developed basically for space research. Another technical spin-off, and I of course have to mention it here. I will give a number of examples here, but be aware that this is just a subset of everything that has been done. And of course I have to select the Swedish example here. And this is coming from a group of scientists that's looked into lung function in microgravity for 2 decades now. And they wanted to look into exhaled nitric oxide. So nitric oxide is a metabolic marker of airway inflammation. And the concentration in exhaled air, when it increases, it's marking then an inflammation, which could be due to a cold, or it could be connected to asthmatic severity, for example. These measurements are not easy. The concentration is parts per billion. So you need very accurate technology. And if you want to do this in space, again, you need to develop a specific machine to do it. And this was done by the Aircrane company here in Sweden, together with funding from European Space Agency. And they miniaturized this technology. You could do the experiment in space, and now this device can be used in an office of a general practitioner or even at home and an asthmatic person. And the thing is that you can here follow the progression of the disease, and you will see that before you get any worse symptoms, you will see the increase in nitric oxide. So it's quite a good help now. And everybody knows about bone loss and spaceflight, of course. It's have been a real issue. Astronaut can lose 1 to 2% of bone mass per month, and that over a 6-month expedition could be more than 10%. And there's different ways how this is done, of course, being tried to counteract this loss. Typically, a lot of exercise, treadmill running, strength training. The problem with exercise in weightlessness is that sometimes it's difficult to provide high load to muscle and bone in a physiological, meaningful manner. But what happened in 2008 was that a new strength training machine was launched called Advanced Resistive Exercise Device. And that allowed very comprehensive, heavy strength training on orbit. And what was seen that up to that point it had been difficult to prevent bone loss. It was still significant loss, even though there was a lot of training. After that point in time, with heavy strength training and proper nutrition, enough energy intake, vitamin D and everything else is properly taken care of, the bone loss decreased significantly. So this was regarded as a breakthrough, basically, and which could be regarded as a bit strange, because it's common sense, right? You should have beneficial effect of loading bone and eating well. The thing is here that the magnitude of the bone protection that was seen here, just from physical load and proper nutrition in a well-controlled population, really inform and emphasize of the importance of these kind of interventions in preventive medicine, for example, in conjunction with preventing bone loss or maintaining bone health in the elderly, for example. Another aspect of bone physiology is related to sodium intake or or regular salt intake. And this line of research started already in the 90s as an accidental finding, as I understand it, on space station Mir in a German experiment where they saw that there was a salt retention in the crew without, in a non-osmotic way. I mean, it was a salt retention without retention of fluid, which has not been seen before, should not be possible. They saw it and they started to investigate it in ground-based models of space flight. And what they then saw is that increased salt intake decreases pH. It increases the acidity in the body. And a low pH has an effect of bone metabolism in a way that bone loses its mineralization. So bone mass goes down with high salt diet. And this was also now confirmed in a spaceflight experiment, again, very controlled astronaut population, periods during flight where they had only low salt diet for a week, high salt diet for another week. They were measuring pH, markers of bone metabolism, and they saw a difference. So this is a very novel and interesting finding. And what's even more interesting maybe is that if it's just pH that is affecting bone like this, maybe it can be counteracted with an alkalinizing agent like bicarbonate. And this is what is being looked into right now. And the immunological system is another interesting area. The immune function in crew changes, it's clear. And in many aspects, it can be said that the function goes down. And there is a lot of research going on because we don't know why exactly. And there are other research that is looking into the effects of the decreased immune function. For example, most of us has dormant viruses in our body, kept dormant by the immune system. If the immune function goes down, will we see virus spreading, virus particles in the body fluid in crew, for example? So this was looked into, and indeed, virus spreading takes place in space. So that was interesting. And what was also here coming out as a tech spin-off is that in order to define concentration of virus particles, you need quite elaborate measurements and PCR technology, which is not easy in a spaceflight setting. So again, a new technology was developed, and this is now used for rapid detection of viruses in a clinical setting. Another example, also now very different, the regulation of body temperature. It's physiology and it's physics. It's physics because if you stand still, the heat of your body will warm the air surrounding the body, and the air will start to flow, and you will have a passive convection, which cools the body. Microgravity, that is not happening. So you will not have that passive convection or cooling flow of air in the same way as on ground. There are other changes taking place, which is physiology. The blood in the body will be pooled centrally and toward the head. There's another blood distribution. And that will probably also affect the temperature regulation. So this led Americans and German scientists to look into this. Again, of course, scientific technology was developed, a non-invasive heat flux sensor that can measure core temperature just by attaching a sensor to the forehead or the chest. And then they assessed body temperature during standardized sets of exercise. And indeed, of course, temperature increases much more when you do a defined set of exercise in weightlessness. And in many cases, it increased so much so that it actually induced fatigue in itself, just an effect of the increased temperature. So that is interesting in view of designing work tasks for crew, but it's also knowledge and it's technology that again is being used in population working in extreme environments, like firefighters, soldiers in warm climate, or miners, for example. And then this we heard about this morning, the rather recent discovery that a large part of the long-duration space flyers get vision impairment. So it's regarded as one of the main medical risks with long-duration spaceflight. So when they started to see this, they investigated, did eye examination, and what they saw was indicating that intracranial pressure might be the cause for these vision changes. The question is, why would they get high intracranial pressure? It can surely not be just the blood distribution, because you have a similar distribution every time you lay down in a supine position. It has to be something else. You could not look in the textbook and find an explanation to this. It's still basically unknown, but there is speculation. Is it the elevated carbon dioxide level on the station? Carbon dioxide widens the brain, the vessels in the brain. Sodium intake with increased blood pressure. Is it this new training device that they can train so hard that they train with a higher blood pressure, and maybe that is creating it? With a lot of speculation, and there is a lot of research going on in this area right now. There is, to my knowledge, not any solution yet, but there is a lot of knowledge that is being gained, as is always the case when you cannot explain the findings that from regular knowledge. So this is one example from a nutrition group in Houston, led by Scott Smith, and he looked into basically metabolites, in this case homocysteine levels in different crew. Now the level of this substance varies depending on the genetic makeup of the person. So there is a genetic polymorphism. That is normal. But what he saw is that those that has a genetic makeup that accumulates this substance, these are the ones that get the vision problem. And the other one don't get it. So this is not saying that you know the reason for the problem, but there is a clue for at least a part of understanding the problem. So this kind of research is going on, and we will for sure have broad implication in clinical settings and also changing textbooks. And I will end with two simple experiments that look very simple, but if you look at the results, it provides basic information for new basic knowledge. So this one, if you look at the picture in the middle there, it's an obstacle course. So this scientist had the crew running an obstacle course around different, in a track, and try to do it as fast as they could. So of course, after flight, they couldn't complete this course as quickly as before flight because of balance issue, muscle coordination, and these kind of things. And they also showed that it takes about 2 weeks to get back to normal. And this is, of course, beneficial to know if you're planning a mission to Mars and a landing, and you try to schedule tasks for the crew when they land on Mars, and they need to be capable of doing it, so you need to know if they are decompensated somehow. But it's also interesting from a learning perspective. Learning and forgetting in the neurological system. And I'm not talking about cognitive learning here, it's basic neurological learning, for example, in the balance system. And this kind of learning curves is very relevant for understanding recovery or rehabilitation of brain injuries, for example, and similar questions. And the final example here is related to an experiment led by a Danish scientist, and he just measured blood pressure, 24-hour blood pressure that is being done on thousands of people every day in diagnostic way. And he found in this group of about 50-year-old astronauts that blood pressure goes down. So he said the conclusion is it's healthy to go to space for your cardiovascular system. But the really interesting thing with this finding is that it shouldn't happen. Blood pressure is the product of the amount of blood the heart is pumping together with the resistance in the vasculature. And we know that the amount of blood that the heart is pumping is increased in space. We know that the sympathetic system with norepinephrine is slightly increased in space, which should give a higher resistance. So what you should see, following the information you have and the textbooks as they are today, is that blood pressure goes up, but it doesn't. So this kind of rather straightforward experiments very often brings very surprising findings in space. So finally, I will just say a couple of words about roadmaps. And these roadmaps of medical research in space typically are connected to preparation for space exploration, human space exploration. So it's about risk mitigation. And it basically, they started because human space exploration, you will have a mission with a biological system and a technological system. And both systems need to work for mission success. If you then, the biological system is putting constraints and boundaries towards the technical system, it becomes complicated, which is typically why you see a lot of innovative solutions in human spaceflight. And it's also the reason why you need to increase the knowledge, the medical knowledge, to understand and define the constraints and requirements coming from the biological system. And this is why you have roadmaps. And I just list here examples of existing roadmaps and a risk matrix of from an international roadmap, where basically a list of various medical risks and color risk matrix, as in usual risk assessment. And the different scenarios in this case is ISS 6 months, going to the moon, going to deep space, or going to Mars. And the message here is that it's right now would probably be medically risky to go to Mars. And with that, I want to say that, of course, I'm not the subject matter expert in all these experiments that I mentioned, but I got the information directly or indirectly from the scientists behind those experiments. And I got a lot of information from the ISS program forum and the HRV program at NASA. And with that, I want to thank you.
So with all the negative results of long-duration exposure to weightlessness, do you think that space agencies should be putting more emphasis now on studies of artificial gravity, either partial or continuous, if we're really serious about going to Mars?
There is a lot of discussion of artificial gravity among the scientific community, and there is also interest from the space agencies, as I understand it. I think it's difficult to answer it right now. It would be good, to be able to counteract the microgravity effects. On the other hand, we're starting to be rather good to counteract it with exercise and nutrition, for example, as well. And there is negative aspects of artificial gravity, as has been very clearly stated also from astronauts' offices, that if with gravity suddenly the small volume becomes even smaller because you cannot work in 3D, stuff start to have weight, and there's suddenly the risk for injuries. So there is positive and negative things, but there is a lot of research going on in artificial gravity.
So we have one more very interesting presentation that I hope you astronauts and cosmonauts will be able to relate to if you think about yourself being on board this spacecraft and entering into a highly unusual environment. The speaker is Andrea Akamatsu, and we met only a year ago at the International Astronautical Congress at a special session called Late Breaking News, and he was speaking about Rosetta, which was just barely in orbit, and Philae had not yet been released for landing at that time. So Andrea, he joined ESA as the Rosetta operations engineer after spending time at Fiat working on the Vega launcher and the Philae lander. And so he was the Rosetta operations engineer up through launch. And then he was placed in suspended animation during the cruise phase. I'm just kidding. He really wasn't. They didn't do that to him. But they didn't give him the few years off either. They reassigned him as the spacecraft operations manager for the Venus Express mission. And so he worked on that Express mission until it was successfully launched for its mission. And then he returned to Rosetta, this time as the Rosetta operations manager and the flight director. So in my parlance, he is what we call flight. And he will be talking to us today about this very interesting trip, and I want you to be thinking about you being on board.
First, just to put things in context, in 2008, I was not even called to become an astronaut, and yes, I wanted to be an astronaut, and I still want to be an astronaut as my former director. I've done a different type of exploration. I was lucky enough to find my way in exploration, nevertheless, not having been called as an astronaut, and I had the luxury to be the flight director for the Rosetta mission. Comets have always been inspiring. Why do we fly to comets? Well, because they inspired the human being since centuries, and it was said today, we have to explore because we want to know more. We want to know what is around us. We want to know how we were born. We want to know how we formed. So this morning, there was a very interesting visualization. We saw all our universe starting from the ISS, going back. Well, comets are somewhere in between where we started this morning and when we ended up this morning with the Big Bang. Comets are surrounding all of our solar system. If we look at this image, our solar system is this part here. This is the orbit of Pluto. It's just that part. There are billions of comets as part of the solar system, but are far beyond what we believe is the boundary of the solar system. We normally set the boundary of the solar system with the orbit of Pluto. Well, it goes well beyond. It's something like that. So why do we want to study comets? Well, because we want to know more how we form, our life form, our planet form. And why do we go to comets? Well, if you look at a building, how do you know what is inside this building, inside these walls? The best thing to do is to go to the building place when the building is being built. You find tiles, pipes, tubes, electrical wires, bricks. Well, comets are nothing else than the leftover or the building place of our planets of our solar system. This is what formed at the very beginning, and then our planets formed. That's why we go to comets. That's why we believe we can understand a bit more how our planet Earth formed, how our planets formed, and our solar system even developed further. So what did we know about comets? Well, not very much before we did Rosetta. There were several missions. One of them was the Giotto mission, was launched in '85 and flew by Comet Halley in '86. These are all what we knew about comets when the scientists decided to launch Rosetta. This was in May '85, even before this mission was launched. Someone was brave enough at ESA to decide, yes, we're going to do another mission, will be a sample return mission. We do it together with NASA. Things changed, things evolved. The sample return mission became a landing mission. NASA partially pulled out of the project. Nevertheless, it took another 10 years to convince ourselves, yes, we can do this mission. Mid of the 90s, ESA decided to put money, put 1 billion euros to fly this mission here, to go to a comet. Took another 10 years to prepare the spacecraft. And this is the end. This is the spacecraft that we launched. It's a 3-ton spacecraft. It's relatively big. This is what we call Rosetta, and this is what we call Philae. It's the lander module that detached from Rosetta and landed on the surface of the comet. These are the sidewalls with the radiators. The solar arrays are not mounted here. This was 3 tons, a bit more than 3 tons at launch. This is the spacecraft we're talking about. Why Rosetta? Well, as the Rosetta Stone allowed our people to understand all languages the same way our scientists want to understand with this mission, with the comet, with exploring the comet, how our solar system formed. Then, well, we have the tough program in front of us. If you were an astronaut on this mission, well, this is what you had in front of you. The target, 67P Churyumov-Gerasimenko. Launched in 2004 in March on an Ariane 5. Arrival date, August 2014, 10 years flight, 6.5 billion kilometers flown. Is it a lot? Well, not very much. We on Earth, we travel much faster than what Rosetta because we are much closer to the sun. We run in the order of 10 billion kilometers here on the Earth during the same time frame. And this is the interplanetary trajectory we did in the course of the 10 years. Unfortunately, our launcher are not powerful enough to launch us straight to an orbit. We didn't want to fly next to the comet. We wanted to reach the comet. We wanted to rendezvous with the comet, something nobody else had ever done. We wanted to orbit the comet, and we wanted to land. What does it mean? We have to go on the same orbit. Same orbit, the orbit of the comet is more or less on one side, same distance as Jupiter, 5 AU. On the other side, a bit more than the Earth. It's 1.24 AU from the sun. So we needed energy. Launchers do not have enough energy. We have to steal this energy somewhere else. And this we did with planets. Many people believe that gravity assist maneuver is what we use to launch the spacecraft. It's not gravity. What we need is energy. Gravity is a conservative field. All the energy that gives you by pulling you towards the planet, when you go away, it takes it back. So you get out with the same velocity. What we are stealing is the energy or the angular momentum of the planet going around the sun. Gravity is just the medium we have used to transfer this energy from the planet onto the spacecraft. We did 4 of these maneuvers in these 10 years of flight, such that we could accelerate Rosetta so far away that we could reach our comet and we could reach it with the same velocity. So we could actually approach it and rendezvous. I just give you one number to have a feeling of what we have done in these 10 years. On board Rosetta, when we launched 3 tons, 1,700 kilograms were propellant to accelerate the spacecraft in the course of the mission of 2.2 kilometers per second. This is the delta V we had on board Rosetta. With the Planetary swim by, we achieve an equivalent delta V of 20 kilometers per second, a factor 10 more than the propellant we had on board. If we had to carry all that as propellant, then we would have ended up with a spacecraft weight in the order of 100 tons, and this would have been even more difficult to launch towards the comet. So, what comes next? Well, we come out of the hibernation in 2014 and we start seeing our comet. This is pictures taken in May last year when we were roughly speaking 2 million kilometers away from the comet. So in solar system perspective, we were already very close. We could see the comet, not only, but we could also see the comet that was already becoming active. Comet is throwing out gas, dust, and we'll see later what this means. We want to orbit a comet, we want to reach a comet, but we know the position of the comet with an uncertainty of 10,000 kilometers. Then we have to resolve this uncertainty. So we start taking pictures of the comet and doing slowly maneuvers that bring our spacecraft exactly where we want. And this is what we did in the course of May, June, and July last year. Instead of having a single orbit insertion maneuver next to the comet and risking of having everything wrong, then we started slowing down relatively mildly towards the comet, and we had split the maneuver in several chunks. I don't go in the details of the maneuver here, I just want you to notice something. Here we go to the scale from million kilometers, hundreds of thousand kilometers, thousands of kilometers, until we reach the comet early August last year. One thing you see, we are approaching it from the direction of the sun. Why? Well, because we need to see the comet. We couldn't approach it from the backside, otherwise we wouldn't see the comet when approaching it. And we needed to see it because we didn't know exactly where it was. So we needed to do this. Then we started seeing our comet. This is July, a couple of thousand kilometers away, and we start seeing a relatively odd shape. We went closer and we found this. This is the comet we found. You see it's rotating as a period of 12 hours. It's an object which is 5 kilometers big. I come back to this later on. Where is it exactly what we were expecting? Well, not really. This is our shape model that we had prepared with the Hubble Space Telescope observation in 2003, and we were expecting something like this. We went there, we almost found two different bodies. For a while, we were speculating whether these were two bodies, and eventually moving compared to each other. If this was a binary system, then we would have had serious problems. Our systems were not ready to characterize and land on a binary system. So this is the final approach. I assume, and I say I assume because I'm not an astronaut, but people that went on the Apollo, when they're approaching the moon, then they saw something similar to this, at least. You see the comet disappearing from the navcam images, the navigation camera that we have on board, exactly because we didn't know exactly where the comet was. I said we had to do maneuver, and we were continuously re-estimating where the comet was and continuously applying correction maneuver to get there. The last maneuver we did before the arrival here was slightly overperforming compared to our prediction, and basically brought us completely off track. We even missed the comet from the field of view of our camera. Was promptly brought back in track, and this is the comet we found when we got there. I repeat, this is an object of, roughly speaking, 5 kilometers size, and this is where we wanted to land. The next problem is, how do we land on something like this? Find a landing place, a safe landing place, a smooth landing place on this object. This we had to tackle. But before getting there, we had to do something else. We had to characterize the comet. When you fly to Mars, or if you have a spacecraft orbiting the Earth, you fly to Jupiter, you know almost everything of these systems. We didn't know anything of the comet. First, we didn't know where it was. We didn't know its mass. If you want to orbit an object, you have to measure the mass of the object, or at least to know. We hadn't the faintest idea what the density of a comet is. We didn't know its shape. We didn't know its spin axis, whether it was spinning, whether it was nutating. The comet is emitting gases. This is ice that is sublimating because of the heat of the sun, and these gases are impinging on the large solar rays of Rosetta. This is wind, and it's blowing the spacecraft away from where it should be. So we had to characterize all these, and this is the orbits we flew at the very beginning. So this is the time when we had characterized the comet, and we managed to go down orbiting the comet itself. I just skip this one and go to the next one. Once you are there, you have to learn to fly around the comet. And I think we did nothing else what the human being did in a couple of centuries more than, we had only 6 weeks to do this. When the human being started going out of his cave or whatever, started to go around, use reference points. There was a river there, a tree there, a mountain there. These are nothing else than reference points. Well, we did the same when we got to the comet. We located some features on the surface, and these were our reference points. In every image we were taking with our cameras, we were using always the same reference points to determine the spin axis of the comet, the spin ratio, and the shape of the comet. The human being wrote maps. We wrote a map of the comet as well. This is our 3D model of the comet. On the left side, you see a real picture of the comet. On the right side, a simulated picture with our 3D model. It's our map of the comet. That's why we could fly around the comet. Then when we started flying, I mean the human being with aircraft, we started using the basic laws of physics to say, if I'm traveling at this velocity and I travel for so much time, then I run for so many miles or many kilometers, where we applied basic physics laws also to orbit the comet the very first time. We assumed that the comet as a single point mass, all mass concentrated in a single point, but we had to measure this mass. So we used the spacecraft as a sensor, and we measured that the comet was weighing, roughly speaking, 10 tons. This is how do we do it? Well, we were flying next to the comet, and the comet was attracting us, and we saw how the orbit of the spacecraft was perturbed by this. The trajectory of the spacecraft was perturbed by this. But at the same time, we didn't know where the comet was, how the comet was rotating. So our estimator, normally when you fly a spacecraft, the problem of navigation is to know where the spacecraft is compared to the object you want to fly around, the Earth or whatever. Here we didn't even know the object, so our variables were many, many more than the usual navigation process. This is our estimator, and this is the masterpiece of navigation we had to do. This was not enough. We had to do much more. We still wanted to land the comet. This is far not enough. As we introduced radio system navigation on aircraft in the 50s maybe, then we had aided navigation. Our operators, instead of looking at images at the famous reference points manually, we had tools developed at the same time that could show us the real images of the comet compared to the simulated one and allow us to identify the features of the comet and know how we were flying. We went farther. Navigation also on the Earth went farther. We have the GPS now. We have satellites. By triangulation, we know where our mobile phone in our pocket is. Well, we did the same on the comet. The only thing the other way around. We're taking images of the comet. By triangulation of the reference points, by now we know where they are. We do triangulation, we know where the spacecraft was when the picture was taken. And this is all automatic on ground. So we downlink the images, we recognize where the spacecraft was, we determine the orbit of the spacecraft. So instead of global positioning system, I call this comet positioning system. And this is the history of navigation in 6 weeks. Now, I was asked as well to give you a feeling of what it means flying around the comet. Good, so I'm not an expert of the ISS, but I try to mention as well something along this line. What do you see on this plot? I could talk for an hour on this plot, but a couple of points. The green line goes on this axis, and this is the distance in kilometers of the spacecraft to the comet from July to October last year when we approached the comet. All the other curves are on this axis. These are accelerations in kilometers per second square, also logarithmic scale. So every jump here is a factor 10. Now, a couple of numbers more. Acceleration on the Earth is 1 EL minus 4 kilometers per second, so it's far above here. It's 100,000 times higher than the acceleration we were observing when next to the comet. Since we're talking about ISS is microgravity. Well, look where microgravity is. Microgravity is 1 to the minus 8, so it's this line here. So if Chris, you said this morning that in microgravity everybody is super happy, here we are talking about picogravity environment. We must be even happier if we explore something like comets and we go beyond the ISS. What did we do? Well, here, early July, you see that the distance to the comet is going below 1,000 kilometers. Look at these two curves here. This is the difference of the acceleration given by the sun on the comet and the one given by the sun on the spacecraft. By doing this difference, we call it third body problem. And this is our estimation of the acceleration imparted on the spacecraft by the comet. So the comet is attracting the spacecraft. There was a time, end of July, early August, when we got to the comet, where this acceleration took over. This is the day we could measure the mass of the comet, exactly by estimating these two accelerations and seeing the effects on the spacecraft trajectory of the comet attracting it. Then we had to go farther. We had to characterize the comet. We developed our navigation system. Another point here, we had to go much closer to the comet. At this stage, we were in the order of 100 kilometers, then 50 kilometers, then we went down to 30 kilometers, and we went farther down to 20 kilometers distance from the nucleus. What was difficult there? Well, the comet is emitting gases. I said earlier on, these gases are impinging on the solar rays of the spacecraft and blowing the spacecraft away from its orbit. So if I'm flying in front of the comet, the gas is emitted towards the sun and is blowing me away. So we went on the terminator plane. The terminator plane is the plane perpendicular to the sun direction. Why? Because I'm pointing my huge solar rays to the sun, which is there, and the gas is coming radial from the comet. It's impinging only on the edge of the solar rays. And this is what we did here. This is the acceleration given by the gases, the aerodynamic acceleration acting on the spacecraft. And you see that despite the fact that we went from 30 kilometers down to 20, the acceleration went down is because we moved from in front of the comet to the terminator plane. This is another. So we had to develop a model, if you want, of the winds that are blowing around the comet. This is almost like doing weather forecast. There's a third point here. When we went down to 10 kilometers and we wanted to land, you've seen the shape of the comet. This is not really a sphere. You can imagine that the gravity field is not particularly well shaped. So we had to model the irregularities of the gravity field. But if we are far away, we cannot distinguish them. These are the irregularities of the gravity field, this black line here. If these are the numbers, these are several order of magnitude below the other acceleration we are observing. So we cannot estimate them. But when we went down to 10 kilometers, then this value picked up. And then we could estimate also the irregularities of the gravity field of the comet. So we had to do all this in 6 weeks. Many people believe that the landing of Philae on the surface of the comet was the most difficult thing we did on Rosetta. Well, for sure it was the most attractive, no doubt. But doing this was far more difficult, far more pressure on us, and technically much, much more challenging. And it's because we have done all this that we could land on the surface of the comet. So we selected our landing site on the small lobe of the comet. This is the target point, and this is our error ellipse. Come back to this later on. This is our timeline. The landing is very passive. It's a ballistic delivery. So Rosetta, the mother spacecraft, is orbiting the comet and is releasing the lander. You see it on the top right in this animation there. This is Philae going down towards the comet. I'm not going to describe the timeline of activity we had around that time, but you can imagine that the most important thing is to deliver Philae at the right time, in the right position, and with the right velocity. Again, a couple of numbers to give you the feeling. The 7-hour descent is written here. If we were wrong at the separation point here with the velocity of Rosetta of 1 centimeters per second, propagated for 7 hours, this is roughly speaking 250 meters. So we would land 250 meters away from where we wanted. You have to understand that what we are doing here, we are basically flying over the Mont Blanc. I also, like Samantha, grew up in the Alps, and for me the comet is like the Mont Blanc. It's 5 kilometers big, it's rocks and ice, and this is what it is. We were flying with our plane, with a washing machine, 100 kilos. We had to throw it out from 22 kilometers altitude, so twice the altitude of an airliner. And we cannot make a mistake with the velocity in the order of 1 centimeters per second. Must be much smaller, otherwise we don't land where we want. So how did the landing go? Well, this is prepare for landing. So this is the lander Philae seen from the mother spacecraft. So I guess who was on the command module for the lunar mission might have seen the LEM going down, something like this. And this I don't speak anymore. These are the images of the landing. Just say that this is going in real time. So if you were an astronaut sitting on Philae, you would see the comet moving like that. Leave it, leave it. It's okay. Leave it. It's okay. Oh yeah. Now the range is 22 meters. $15 now. We'll stop at 9. So this is the last image we've taken from Philae when going down. The resolution on the surface of this image is roughly 1 centimeter per pixel. So what you see, there are pebbles and boulders, small boulders that are on the surface. Now, most of you for sure know that something went wrong. When we went there to look where Philae was, then we found this footprint, and Philae was not there. So before we look into where Philae is and what happened afterwards, I think I don't say anything completely wrong if these two footprints are comparable in the history of space exploration. Now, what happened on that day? Well, this is where we were left. Our target point, our error ellipse, roughly speaking, 500 meters in radius. This was the very worst case. We never wanted to come even close to that. And this is where Philae touched down, was 110 meters away from the target point. So you might imagine that our error in velocity at separation was in the order of 1.7 millimeters per second of an object orbiting another object at a velocity of 30 centimeters per second, both traveling at 15 kilometers per second in the solar system at 500 million kilometers away from us. This is what we have done on that day. Philae did an anchor. We saw it flying away. This was the last point where Philae was observed in flight. When after it bounced on the surface, the anchoring system couldn't anchor. Basically bounced away. The gravity, we're in a microgravity environment or picogravity environment, if you want. So Philae was flying away, went up to 1 kilometer's altitude, and landed somewhere else after having tumbled a couple of times on the surface of the comet. We know that Philae is somewhere there. We perfectly know that it's there. We haven't seen it yet. We do not have a single image that tells us Philae is there. Philae operated for 3 days on the surface of the comet and started sending us fantastic images. This was already shown by Jean-Jacques. This is the scientist that basically is responsible for this camera says, this is 80 centimeters away from my camera. My camera is 20 years old. This is 4.5 billion years old. So this is what we have been doing with Philae. This is another image of another rock close to Philae. It was in the dark, so this is largely stretched, the image, and you see the cracks and the rocks that are there. The comet is not only Philae. The mission is not only Philae. The main scientific mission is Rosetta itself. The orbiting spacecraft. Philae lasted 3 days, did its own operation. And what we did is basically we continued operation. We managed to fly even closer to the comet. The image here is taken from a distance from the surface of roughly speaking 6 kilometers. So you see several details. And what you see here is a video of this close flyby. What you see, this is the shadow of Rosetta on the surface of the comet. So we managed to capture, we flew the subsolar point and we managed to capture our own shadow, something I would have never believed would be possible. Now, the comet becomes more active, it gets closer to the sun and it starts throwing out more and more gas. At the beginning, when we reached the comet, we were measuring 3 kilos per second. Now we are measuring in the order of 300 kilos per second. This is all dust and gases which are coming out of the comet. And you see the jets here in this video taken by the OSIRIS science camera. These jets are disturbing the trajectory of the spacecraft, but not only, there's much more coming out of the comet. There are boulders coming out of the comet, so the comet is sort of cracking and modifying itself. So we keep track of these things. Next year we want to fly closer to the comet when it will go again away from the sun and we want to explore it. I want to show you one last image. This is a snowstorm. This is what the star sensors of Rosetta sees in the sky when it's flying in the environment of the comet. So you can imagine that there's an environment that is very, very active. It's not easy to distinguish the stars in something like this. And these are the dust particles that one of the instruments has collected. So dust particles are continuously hitting the spacecraft. We are collecting them and they are exploring them. So this concludes my presentation. I have the selfie of Rosetta. I have another picture of Rosetta with a massive jet we observed only for a few minutes on the surface of the comet. The mission is still very active. We want to, as I said, we want to continue till September next year, and we want to go even much closer to the comet, and we will land the spacecraft on the surface of the comet next year. So stay tuned. There might be much more coming out of this mission. Thanks a lot for your attention.
I have two questions, one very short, and that is if you can give us the bulk density that you determined for the comet overall. That's a simple one. The second one, a little more difficult, and that is in the asteroid area, which I'm in particular very familiar with, we have no trouble whatsoever when we see something morphologically, as we've seen here, to talk about a contact binary. But in most of the recent scientific presentations on Rosetta, there seems to be an avoidance of the idea that this is two different objects that have come together and maintained contact and therefore formed the neck of the duck, as you've been calling it recently. And I'm wondering why the difference in approach. Why has the idea of a contact binary not been the primary explanation for what we're seeing there? So if you would first, just the bulk density.
The density is roughly 0.4, so actually I should have mentioned, if you pick up the comet and you throw it in the ocean, it floats. It weighs 0.4 instead of 0.4 instead of 1 than water, so it's much lighter than water. On the second,
a cork.
Yeah, more or less. On the second question, I'm afraid I'm an engineer, I'm a flight engineer, and I do operations. So this is a question for the scientists, and I'm sure you will find scientists that will tell you that your theory is right, and scientists will say another thing. I don't know. I must admit, I don't know. We at the beginning, we feared there was a contact binary, but the most up-to-date theory doesn't say that. But why this is, I'm afraid you have to ask the scientists. Sorry.
Okay, thank you for your presentation, and also thank you for the very impressive landing you did. I mean, I saw that live, but it was pretty exciting. But you seem to be more excited, I'm guessing. Anyway, I'm hoping my question is not poorly timed, since firstly, it's not a technical question, and secondly, we've just seen a very impressive accomplishment. But my question is regarding ESA, and regarding space industry in general. Now that it's becoming larger and also a lot more, in some regards, conservative and maybe a bit more bureaucratic. And this is, of course, just my personal view. And ESA also is seen sometimes as a bit conservative. And all organizations that become larger can become a bit more conservative. As Jean-Jacques said, the world is going faster, but the decisions are going slower.
So what is your question?
Yes, my question is, thank you. Do you think that could be a threat and a problem for the space industry in the future? And do you believe private industry could have a solution to it, more or less?
I cannot tell you the solution. I also sometimes have the feeling that, at least I speak for ESA, we are becoming a bit too bureaucratic. I have no doubt. I think we have to consider that this is a normal process for a public organization. I'm not aware of any public organization that became lighter and lighter over time. Actually, they tend to become heavier and heavier. And it's a task of our directors, of ourselves as well, to renew this process, to reset it. And for sure, we have to do it. Otherwise, we cannot embark on a trend and not stop it. We'll collapse. So we have to do something. I don't think we are in danger now, but we have to keep it under control.
This rendezvous and docking, or rendezvous, is a masterpiece of orbit mechanics. However, what is the current knowledge of ESA why it didn't succeed to grab on the surface? So actually it should grab and hold on the surface and didn't do that. So what's the current understanding why it failed?
Yeah, we have evidence that there are two harpoons which were fired by actuators, and these actuators didn't work. Why they didn't work, we don't know exactly. We have a couple of speculations. But since we never managed to control Phil, we regained contact with Phil in June, July this year, but we got only telemetry, could never control. We couldn't really...
What about the harpoon?
This is what I meant, the
harpoon. They did not fire.
They didn't fire.
Right.
Both.
And last question.
So related to that, when the spacecraft touched down and then bounced off, did you get an accelerometer measurement that told you how soft or hard the surface was?
Yes. Well, part of the scientific instruments is acceleros in the feet of the lander. They speculate that they could sink for something between 20 and 30 centimeters on relatively soft dust. And then they hit something very, very hard, much harder than expected. That's why we bounced away. We landed 1 meter per second, and we bounced away with 38 centimeters per second, and the escape velocity is 50 on the comet. So we went very close to go back.
Yes.